methods, and of course, I forgot 2 slides, which I will go over quickly. So I finished with that slide, but that was a mistake. There were still 2 more slides. So I mentioned that you could use local methods in a slightly more sophisticated way than just looking at congruences. One of these methods is Strassman's theorem. It's very classical. And it's a very cute theorem and very simple to prove. It's an excellent exercise in ultrametric inequality. The theorem says the following. If you have a power series, sigma of Fn x to the n, where the coefficient tend to 0, theoretically of course, and which is not identically 0, then you have an upper bound, unfortunately not always sharp, on the number of elements of Zp which are roots of f of x equals 0. And what is this bound? It's the unique integer such that all of the absolute values of the coefficients of the power series are less or equal to Fn, and n is the largest integer with this property, meaning that the absolute value of Fn is strictly less than the absolute value of Fn when n is larger than n. It's really an easy exercise, and it's very amusing. It's valid just the same in extensions of QP. And here is an example of use. Let's assume we want to solve the equation x cubed plus 6y cubed equals 1 in the integers. The natural field in which to work in is the field Q of theta, where theta is a cube root of 6. It's easy to compute that the fundamental unit is epsilon equals 3 theta squared minus 6 theta plus 1. It's of norm 1. And Dirichlet's unit theorem, well, I agree that, properly speaking, I'm not talking of local methods here, but still, since it uses Strassman, it's local. Dirichlet's unit theorem tells us that x plus y theta is going to be a power of epsilon. There is no sign. Epsilon to the k for some k in z. So we write epsilon, you see, is congruent to 1 mod 3. So I write epsilon equal to 1 plus 3 alpha, alpha being theta squared minus 2 theta. And I look at the power series 1 plus 3 alpha to the k, but warning, I'm not looking at this power series as a power series in alpha. I'm looking at this power series as a power series in k, in the exponent. So in fact, you better look at the right-hand side, which is the 3-adic exponential of k times the 3-adic logarithm of 1 plus 3 alpha. Anyway, this power series in k converges 3-adically. It's trivial to prove. And in addition, 1 theta and theta squared are linearly independent over Q3, which is equivalent to saying that x cubed plus 6 is irreducible in Q3. And so what we need, you see, is simply to have an element which has 0 theta squared coordinate. You write epsilon to the k equals x plus y theta plus 0 theta squared. So you need the coefficient of theta squared to be equal to 0. This gives an equation in k, which is exactly an equation to which we can apply Strassman's theorem. We find, by computing the coefficients explicitly, that capital N equal 1. And since we know a trivial solution, which is k equals 0, that means it's the only solution. So the only solution to our Diophantine equation is 1, 0. You can, in fact, apply this method more generally to any equation of the form x cubed plus dy cubed equals 1. Okay, that was the 2 slides I forgot to mention yesterday. Okay, so we go on now to what I call the naive method of solving Diophantine equations. So now we start with global methods. So the naive method is factorization over z. We don't use number fields. And one method I would like to explain, because it's fun and it's not so well known, although completely elementary, is what's called Bent's criterion. It's a criterion for the first case of Fermat's last theorem, which is much more powerful than the Kummer criterion using regular primes, because contrary to Kummer's criterion, which only applies to regular primes, this one applies to all primes. Unfortunately, I don't know how to prove this statement. I'll say more about this later. But it certainly should prove FLT1 if analytic number theorists knew how to prove results that they don't know how to prove for now. Anyway, of course, thanks to whiles, we don't need that, but still, it's so elementary. So let me explain the theorem. Let's take an alpha prime, of course, for ma. You take k an even integer, and you assume that q equals k times p plus 1 is a prime number which doesn't divide this quantity. So the first factor is k to the k minus 1, okay, that's clear. And the second factor, you all know about now since the lectures you've heard yesterday and today, is the resultant. But that's just an ordinary one variable resultant of x to the k minus 1 and x plus 1 to the k minus 1. This is something very easy to compute for any value of k. So you assume that q does not divide this, then FLT1 is true. So the equation x to the p plus y to the p plus z to the p, it's better to write it in a symmetrical way in this form, equals 0. It implies that p divides x, y, z. So if p does not divide x, y, z, it's impossible. So you see, it's a very, very simple proposition. And I repeat, I will repeat it afterwards. This criterion, the existence of a k, it's always true that there exists such a k, except that analytic number theorists don't know how to prove it. So this, in fact, proves FLT1 in practice. So I describe here the proof in the slides. I guess it's probably one of the only proofs I will give, but it's so simple. So I'll go relatively fast on the proof. Just believe me, but of course it's in the notes. So I just want to insist on the fact that you just factor over z. Normally, when you attack Fermat's last theorem, you factor y to the p plus z to the p over the cyclotomic field q of z to p. Here, you just simply put y plus z as a factor. And you get this, of course, minus x to the p equal this factorization. It's immediate to see that the two factors are relatively prime. Otherwise, y and z wouldn't be. Because, of course, we can assume that x, y, and z are relatively prime, as usual. Hence, since the product is a p power, each one is a p power, so you have y plus z equal a to the p, and the big polynomial is also equal to some power, which I call s to the p. And since I wrote the equation in a symmetrical way, x to the p plus y to the p plus z to the p, of course, this is true for z plus x and x plus y. Z plus x is b to the p, and x plus y is. So, if I write the equation, you see, q equal k times p plus 1, well, q minus 1 over k is p. So our Fermat equation is x to the p plus y to the p and so on. So I can write it like this, x to the q minus 1 over k plus and so on. And I just simply say that it's congruent to 0 mod q. Don't even need. Well, if you look at this, it's immediate that if q does not divide x, y, and z, then if you set u equal x divided by z to the pth power modulo q, then you will immediately see that u to the k is congruent to 1 mod q, and u plus 1 to the k is congruent to, oops, that's a misprint, excuse me. It's u plus 1 to the k congruent to 1 mod q. I wrote 0 mod q, it's a 1. I cannot point on my... Okay, here it's u plus 1 to the k congruent to 1 mod q. So this means that u is a common root modulo q of the result of the two polynomials x to the k minus 1 and x plus 1 to the k minus 1. So q divides the resultant, contrary to the hypothesis. So it's not possible that q does not divide x, y, z, so q has to divide x, y, z, and the equation is symmetrical, so I can assume that q divides x. And by writing this very subtle sequence of congruences and inequalities, you see, replacing x plus y and z plus x and so on by p powers, I get this remarkable identity, no, I'm joking here, of course, involving a, b, and c now instead of x, y, and z. 0 is congruent to c to the p, well, q minus 1 over k, plus b, plus minus a, mod q. And so we're back to exactly the same equation as above. Excuse me, not equation, congruence mod q. So exactly the same reasoning tells you that q divides ABC. But since we know that q divides x, and x, y, and z are pairwise coprime, we cannot have q divides b to the p or q divides c to the p, so you have to have q divides a. Okay, you see, I know I'm going very fast here, and probably you can't follow, but you see the level at which this reasoning is. It's really totally elementary. So you have y congruent to minus z modulo q, and now we replace in the big equation, you know, the y to the p minus 1 minus and so on, which I call the s to the p. S to the p is congruent to p y to the p minus 1 mod q. I use the fact that y is equal to x plus y minus x, so that's congruent to c to the p mod q. And finally, you mix all this together. Well, I'll skip what you get. And you finally get that 1 is congruent to k to the k modulo q. And we assume that q does not divide k to the k minus 1 contradiction. So I know I went fast, I repeat, but you can see the level of this proof. There is nothing. We've just did congruences modulo q and factored over z and just used the fact that z is a unique factorization domain to say that if a product of two coprime things is a p power, then each one is. End of proof.
Excuse me.
Yes?
Are these k's very common?
That's the next slide. So although Ven's criterion is superseded by Wiles, it's a very powerful method since heuristically there will always exist a suitable k, and I made a computer search, and of course I always found such a k, and usually you find k very, very small. I mean, it's rare, very rare that you need k larger than 100.
What is the heuristic?
That's the whole point. Analytic number theorists are not able to prove this.
Right, but why do you assert that? What is your heuristic for saying there's always one?
Well, my heuristic is that on probabilistic ground, it's really highly plausible. I mean, if you look at the conditions are really very, very mild. I mean, you just ask for non-divisibility, and it's really, in fact, I'm not an analytic number theorist, and I must say I'm quite surprised that the tools that we have in analytic number theory are not able to prove this. Because you see, here, well, in fact, let me state the corollary, which was due to Sophie Germain before Ven's criterion. If you simply assume that 2p plus 1 is prime, then FLT1 is true. That's a special case of Ven's criterion. And here, of course, that I know sufficiently analytic number theory to know that this is, of course, completely inaccessible with tools from analytic number theory now to know that there is infinitely many pairs, many primes such that 2p plus 1 is prime. This is really inaccessible. I mean, it's at the level of Goldbach conjecture, p and p plus 2 prime, or so on. On the other hand, Ven's criterion is so much weaker than that. I mean, we just need a k such that kp plus 1 is prime, and this, of course, exists by Dirichlet's primes in arithmetic progression. But, of course, we have this little extra condition on k to the k minus 1 and on the result. Anyway, so that's, I just wanted to show you Ven's criterion because it's not so well known, and it's really so easy. So let's come now to another equation. I'll just spend one slide on it, I guess. The equation y squared equal x cubed plus t. That's an equation which really many, many, many famous people have worked on, and it's far from being solved. But I can show you some very easy results. I'm not proving them, but you can consider them as exercise, because really it's much easier than Ven's criterion. I mean, you just sit down with a pen and prove it at lunch. I mean, it's really very easy. So for certain values of t, it's very easy to solve. For others, it's much more difficult. So here are two examples. Consider this as exercise. If a and b are odd and b not divisible by 3, then if you take t of the form 8a cubed minus b squared, if t is square free, then this equation doesn't have any integral solutions. And that's a general case, it's a generalization of a challenge posed by Fermat for the case t equals 7, to show that y squared equal x cubed plus 7 didn't have any integral solutions. A similar exercise, if you assume only a odd and b still divisible by 3, not divisible by 3, now you take t equal a cubed minus 4b squared. You still assume that t is square free, but you also assume that t is not congruent to 1 modulo 8. Then again, it has no integral solutions. I'm not giving you the proof, but really, I mean, you can sit with a piece of paper and it's absolutely immediate. But I repeat, it's really quite we're quite happy to have this kind of results, because if I take a T which is not of this form, then it's much, much more difficult in general. And I have a whole chapter on this, a whole section on this in my book for those of you who downloaded what I put on the web. Okay, now I'm going to spend a good part, well, a good 15 minutes or more, telling you about Catalan's equation in, still, it's an application of factoring over Z. Now, as I said, Catalan's equation was solved completely by Mihailescu, and the proof is extremely pretty, although parts of it are very technical. I gave a course last year on this at l'École Polytechnique in Paris, so my goal is not to prove it here, because that would really have been a course in itself. But I just want to show you the results found by Cassels in 1960 on Catalan's equation. I want to make two comments about this. First of all, I would like to thank René Schroff for simplifying for me one of the arguments of Cassels, which was too technical originally. And second, the first theorem proved by Mihailescu on Catalan's equation is a theorem which is extremely similar to Wieffrich's criterion for the first case of Fermat's last theorem, 2 to the p minus 1 congruent to 1 modulo p squared. And surprisingly, I mean, for me, it's quite impossible to understand why it wasn't done. The proof of Mihailescu's result is so simple that I don't understand why it wasn't found just after. Of course, it uses Cassels' results, but I don't understand why it wasn't found just after Cassels' results, because it's exactly the same. In fact, it's even simpler than the proof of Wieffrich. So it had to wait for 1998 or 1999 to be found. And I don't understand why. I mean, it's really very simple. Unfortunately, I cannot talk about this subject here for lack of time. But it's explained in my book, but not in the part I have put on the web. So Catalan's equation is x to the m minus y to the n equal 1, m and n both greater or equal to 2, including 2. And that's also quite an amusing thing, because it's not so easy for 2. For n equal 2, so the equation x to the m minus y squared equal 1, there are no integral solutions, no non-trivial solutions. And this was proved by Victor Amédée Lebesgue in 1850. And this is not the Lebesgue of the Lebesgue integral. Initially, I thought, but it's not. And the proof involves factoring over, not over z, but over z of I, and it's not difficult at all. On the other hand, the proof for m equal to x squared minus y to the n equals 1 is much more difficult. Well, much. It's more subtle. And in fact, the only reason why it's more subtle is because in that case, there are solutions. It's always simpler to show that the Diophantine equation doesn't have any solution at all than to show that the set of solutions is exactly the set that you know. And in this case, there is the solution 3 squared minus 2 cubed equal 1. And this was proved by Ko Chao in the 1960s. And, well, it doesn't use very sophisticated things. It involves the structure of the unit group of a real quadratic order, which is not necessarily maximal. So this is not really very deep mathematics, but it's clever. So thanks to these two cases, which I'm not explaining, we're reduced to the case where the exponents are primes, as usual, x to the p minus q equal 1, where p and q are distinct odd primes now. And thanks to the fact that they're odd, we now have a symmetry, which we didn't have before. We can change p, q, x, y to, we can interchange q and p if you exchange y, well, if you change x into minus y and y into minus x. So we will use the symmetry at length in the work on Catalan's equation. So the basic results on this were found by Cassels in the 1960s. And it involves essentially 3 lemmas. One is an arithmetic lemma and 2 analytic lemmas. Well, 2 lemmas of Diophantine approximation, should I say, not analytic. Plus, of course, clever reasoning. So the analytic lemmas are, in a sense, included in what's called Runge's method, which is, well, Runge's method can be explained in very simple and also in very sophisticated terms. But I just give you an exercise on Ringer's method, which is really a toy exercise, but still you can try your luck at it at lunch, but it's really very, very simple. Solve the Diophantine equation, y squared equal the fifth cyclotomic polynomial, x4 plus and so on, plus 1. Find all values of x for which integral values. We're talking about integers here, not rational numbers. It's very easy, but there are hints in the notes, but it's really very easy. So that's really the toy example of Runge's method. So the arithmetic lemma is the following. You take a prime q, and you set w of j equal j plus the valuation of j factorial, which is, of course, well known. It's j minus the sum of digits of j divided by q minus 1. Then the lemma tells you that if you take the binomial coefficient p over q j, the exact power of q, which divides it, is minus w of j. So q to the omega of j, p over q j, is in fact, well, it tells you a little more than that. It tells you that it's an integer coprime to q. So not only that it's the exact power of q, but in fact it's an integer. And in addition, this lemma tells you that w of j is strictly increasing. That's pretty trivial. And the proof is easy, but there is a slight subtlety. So I invite the students to prove this statement, not so much about the power of q, which is really immediate, but about the fact that it's an integer. The fact that it's q integral is easy. But why is it an integer? Why is it in z? That's fun. And then we need two analytic lemmas. One of them is a very easy undergraduate exercise. You take q and p strictly positive real numbers. Well, in fact, they will be our exponents of Catalan, but we don't need that here for the first one. And you take some real number a greater or equal to 1. Then you have a to the q plus 1 to the p is strictly less than a to the p plus 1 to the q. And if a is not equal to 1, then you also have a to the q minus 1 to the p, strictly greater now than a to the p minus 1 to the q. That's an excellent undergraduate exercise, very easy. The second analytic lemma is the lemma which was given to me by René, which simplifies the proof of Kessel's. Assume now that p is strictly greater than q, and really that they are integers, and that q is greater or equal to 3 and p greater or equal to 5, as in Catalan. Since p and q are odd primes, if I assume, well, since they are odd primes, q is greater or equal to 3, and since p is strictly greater than q, p has to be greater or equal to 5. But I don't assume that they're primes, but what they will be. Okay, now I consider this complicated function, f of t. 1 plus t to the p minus t to the p, the whole quantity raised to the power 1 over q. You can write, of course, the Taylor expansion of this thing around t equals 0, because, of course, around t equals 0, inside it starts with 1 plus p times t plus and so on, raise it to the 1 over q. And I set m equals, this has to be extremely precise, the integer part of p over q plus 1. So it's the smallest integer which is strictly larger than p over q. And I call f sub m of t the sum of the terms of the Taylor series expansion of degree at most equal to m of this function around t equals 0. Then the lemma tells you that for all real t between minus 1/2 and 1/2, so absolute value of t less than equal to 1/2, then the approximation of f of t by this polynomial, I mean the partial sum of the Taylor series, so f of t minus f m of t, is bounded by this expression which you see here, t to the m plus 1 divided by 1 minus absolute value of t quantity squared. This is not so easy. But, okay, the proof is in the notes. Of course, it's an undergraduate exercise. It doesn't use any higher mathematics, but still it's not so trivial to do. So thanks, René, for this. So now let's go to Kessel's proof. So as I said, we just factor over z. So how do we factor? Well, x to the p minus y to the q equal 1. We put the minus 1 on the other side, so it gives y to the q equal x to the p minus 1. I simply factor x minus 1 off this x to the p minus 1. So I write that it's x minus 1 times what I call r sub p of x, which is, of course, x to the p minus 1 plus x to the p minus 2 and so on plus 1. I'll never need the explicit value, so x r p of x is that. The factors are not necessarily coprime. And in fact, Kessel's results is that the factors are not coprime. But that's what we're going to prove. However, if you expand Rp of x, which you can write like this, x minus 1 plus 1 to the p minus 1 over x minus 1 by the binomial theorem, it's immediate to see that p divides x minus 1 is equivalent to p divides Rp of x, that the GCD of x minus 1 and Rp of x is either 1 or p, and that if the GCD is equal to p, then that will be an essential condition. Rp of x is in fact congruent to p mod p squared. That's completely trivial if you look what Rp of x is, because it's x to the p minus 1 plus x to the p minus 2 and so on. And since x is congruent to 1 mod p, well, okay. Easy exercise. And the consequence of this is in particular that the p-adic valuation of Rp of x is exactly 1, not more. And since y to the q is equal to x minus 1 Rp of x, the condition d equals p is equivalent to the fact that p divides y, of course. And the theorem of Kessel's is essentially that we always have d equal p. We never have d equal 1. The factors cannot be coprime. So how does one prove this? Well, of course, we will reason by contradiction. However, it's essential to distinguish the cases where p is strictly less than q from the case where p is strictly greater than q. P equals q is not possible. So the case p strictly less than q is quite easy. So the result of Kessel's is the following. If you take x and y, non-zero integers, p and q odd primes, satisfying Catalan, then when p is strictly less than q, p divides y. So that means x minus 1 and Rp of x are not coprime. So assume that they are coprime. So if they are coprime, since the product is a qth power, each is a qth power, and I just write x minus 1 equal a to the q. Now look at the proof. It takes 4 lines, really very simple. A cannot be equal to 0 because x is not 0. A cannot be equal to minus 1 for similar reason because q is odd. Oh. Okay, and of course, replacing x in the formula, I get a to the q plus 1 to the p minus y to the q equal 1. So I introduced the function f of z equal a to the q plus 1 to the p minus z to the q minus 1. It's trivially a decreasing function of z. Now, let's assume for the moment, for instance, that a is greater or equal to 1. Then on the next slide, I'll assume that a is negative. If a is greater or equal to 1, f of a to the p, see the function f of z, it's a to the q plus 1 to the pth power minus a to the pq. I replace z by a to the p minus 1. And if you expand this by the binomial theorem, since a is strictly greater than 0, this is strictly positive. On the other hand, if you replace z by a to the p plus 1, you get this expression, a to the q plus 1 to the p minus a to the p plus 1 to the q minus 1. And remember the analytic lemma which I mentioned, the first analytic lemma. It says that this quantity a to the q plus 1 to the p is strictly less than that. So, consequence, af of a to the p plus 1 is strictly negative. Okay, well, it's impossible because f is strictly decreasing, and for a to the p it's positive, for a to the p plus 1 it's negative, so there is no integer in between a to the p and a to the p plus 1 contradiction. You see, the proof is really... So that's for a positive, and for a negative, it's a completely similar reasoning. I skipped, I mean, it's exactly the same. Again, by using the first analytic lemma. So this proves the case where p is less than q. To treat the case p larger than q, we need a corollary due to this person, which I wrote here. I have no idea how his name is pronounced. Hero, I don't know, somebody know? then this corollary tells us that under the conditions of, that I had, p less than q, then in fact y has to be really large. Y has to be greater than p to the q minus 1 plus p. And the proof is really very simple, but uses in an essential way what I said, that the valuation of Rp of x is equal to 1. So look, since we have proved now that p divides y and that the valuation of Rp of x is 1, we can write, we must have x minus 1. X minus 1 must swallow all the powers of p which remain. And the powers of p was p to the q. So x minus 1 must be p to the q minus 1 times p power. So p to the q minus 1, a to the p. And Rp of x, the quotient here, must be p, only p, since its valuation is 1, times a cubed power. And y is equal to PAV. That's an immediate consequence. So I set capital P of x, let capital P of x be this polynomial, x to the p minus 1 minus p times x minus 1. It's clear that x minus 1 squared divides p of x. You just compute p of 1 and p prime of 1. And from this, we deduce that x minus 1 divides this quantity, which I wrote, x to the p minus 1 divided by x minus 1 minus p. And this is p times v to the q minus 1. Now, x minus 1 is divisible by p squared, so that means, by p to the q minus 1, excuse me. So that means that v to the q minus 1 is divisible by p to the q minus 2. So v to the q is congruent to 1 modulo p to the q minus 2. Now, it's an elementary exercise in z over nz star, if you've never seen this in your life, to show that since q is strictly greater than p, the Euler phi function of p to the q minus 2 is coprime to q. Hence, this congruence implies that v itself is congruent to 1 modulo p to the q minus 2. That's a completely trivial exercise in number theory. On the other hand, that's a slightly different proof, which I didn't include here, but which is in the notes. In 2 lines, you can show that v equal 1 is not possible. Hence, since v is congruent to 1 modulo p to the q minus 2, and v cannot be equal to 1, v is greater or equal to p to the q minus 2 plus 1, and you replace in the formula for y, which is y equal PAV, and you get that y is greater than p to the q minus 1. I repeat, all this is really very, very down-to-earth mathematics, but of course it's very clever. The case p larger than q is considerably more difficult and really uses Diophantine approximation. As I already told you, Diophantine approximation is only a single statement. The fact that a real number strictly less than 1 is, which is integral, is 0. Well, that's exactly what we do here. Now, let's see, how does the time go? I'm just wondering whether I'm going to go through this in detail. Maybe not. I'll just skim through it. So we want now to prove the same thing when p is larger than q. So again, we assume by contradiction that p does not divide y, so that x minus 1 and Rp of x are coprime. So x minus 1 is a qth power. Y to the q is equal to this quantity. But now I write y as a to the p times this function of 1 over a to the q, where f is that complicated function I introduced, which was the power 1 over q of exactly what is written here, a to the q plus 1 to the p minus 1. Exactly like in the analytic lemma, in the second analytic lemma. And I recall that m is the smallest integer larger than p over q. Now, the crucial object to introduce to do Diophantine approximation is this number z. Z equal a to the m times q minus p times y minus a to the mq times f sub m of 1 over a to the q. I remind you that f sub m is the mth approximation to f. So you see those two quantities. Now, before going any further, m is strictly greater than p over q. So m times q minus p is positive. So the first, and y is of course an integer, so this a to the mq minus p times y is an integer. On the other hand, by the results, if you expand, of course, by the binomial theorem, here I'm skipping, it's easy to see that the second quantity is also an integer up to multiplication by suitable power of q, which I gave you in the arithmetic lemma. And this suitable power of q is written here. It's simply this big capital D equals q to the m plus the q-adic valuation of m factorial. So it's some big power of q. And if you multiply d by z, it becomes an integer. So first slide is the proof. Well, it's immediate. I mean, you just expand by the binomial theorem, the generalized binomial theorem, and say that the binomial coefficients p over qj, you need this power of q to make them integral. So the first statement is that d times z belongs to z, is an integer. The last line. I make another statement, which is that in fact d is the optimal denominator. I will have to use this in the next slide. No lower power of q can give you that. Now we use the analytic lemma. We're going to prove, since we want to do Diophantine approximation, that d times z, although it's an integer, is strictly less than 1. Well, okay, bear with me. You see, you have sequences of inequalities which follow from the analytic lemma, and you need Hero's, whatever his name is pronounced, corollary, which tells you that x is very large. Here it's x and not y because I use the symmetry. So it's in fact x which is going to be large. X is greater or equal to q to the p minus 1. So using all this and mixing everything, I prove, well, just don't read. I mean, okay, you see the proof is really not difficult. You prove that this quantity is strictly negative. And finally, this proves that the absolute value of d times z is strictly less than 1. The details don't matter. But I just want to say that you have to use, of course, Hero's corollary to say that x is sufficiently large. So dz is an integer, and it's less than 1, so it's 0. That's Diophantine approximation. And as I said, d is the optimal exponent of q, which will give you 0. So in fact, you have 0, which is equal to dz, which is in fact congruent to d times the binomial coefficient. Just read the last line. The binomial coefficient p over qm, which is not congruent to 0 mod q, since d is the exact exponent, and we get a contradiction. End of proof. So you see, this is a little more subtle, but doesn't really use very deep things. But that's the results of Castles, and absolutely beautiful, and absolutely essential for the rest of the proof by Mihailescu. So the consequence of this, and this is the starting point for Mihailescu's proof, if you take a Catalan quadruple, x, y, p, q, then there exists integers a and b, and positive integers u and v not divisible by q and p respectively, such that you have these beautiful equations. X is equal to q times b times u. X minus 1 is the power of p to the q minus 1 times the qth power. X to the p minus 1 over x minus 1 is p times the qth power. And exactly by symmetry, you have exactly the same thing for y, except that the minus 1 is replaced by plus 1. It's y plus 1 and y to the q plus 1. So those are Castle's equations for Catalan. And that ends the easy part of Catalan. Now, from there, Mihailescu starts, and the first thing that he proves is the double Wieffrich condition. He proves that this implies that p to the q minus 1 is congruent to 1 modulo q squared, and q to the p minus 1 is congruent to 1 modulo p squared. And what is very pretty in that is that there is no class number condition. There is absolutely nothing, and the proof is really very easy. But it involves a tool which I don't understand why people didn't think of using it, because in fact, it was used for Wieffrich criterion in 1909. So why didn't people use it afterward? It uses Stickelberger's ideal, which is an extremely classical tool. In fact, I will come back to this. So that's the end of factoring over z. So I don't want to insult this audience, still, I will assume that for 2 minutes that you don't know what a number field is. For number theorists, it's of course not plausible, but bear with me. I mean, there may be a few people here who don't exactly know, so I'll just, well, if you want, I can skip the slides. But it won't be long. So now, factoring over Z was a little naive, although it did give us some quite spectacular results as Vent's criterion for FLT1 and the Kessel's results for Catalan. But the real the real stuff where one attacks Diophantine equations is factoring over number fields, and that's what gave Kummer's results for FLT, for instance. So let me recall basic facts about number fields. So it's a finite extension of Q, and by the primitive element theorem, you can write it as Q of alpha. An algebraic integer is a root of a monic polynomial with integer coefficient. The element alpha can always be chosen as such. The set of algebraic integers form a ring. Zk contains Z of alpha with finite index, and it's a free Z module of rank n equals the degree of k over q. A Z basis is an integral basis. The fundamental fact is that the ring of integers Zk is a Dedekind domain, and as an essential consequence is that any fractional ideal can be decomposed uniquely into a power product of prime ideals. And this is the main motivation of introducing this, because the crucial fact is that if you just consider naively Z of alpha, and that if Z of alpha happens to be different from Zk, then it is not a Dedekind domain. Never. In no case. A non-maximal order cannot be a Dedekind domain because it's not integrally closed. So if P is a prime, you have a prime power decomposition, of course, as any ideal. The primes Pi are called the prime ideals above P. The EIs are the ramification, whatever, indexes, I don't know exactly the name. The field Zk divided by Pi is a finite field containing, of course, f sub P with a degree, which is called the residual index, I guess, f sub I, with the relation sigma of EI Fi equal n. Okay, all this is extremely classical, but we need it. Now, the basic objects with which we work on Diophantine equations is the class group and the unit group. So the class group is the quotient of fractional ideals by principal ideals. By Dirichlet's theorem, it's a finite group, and its cardinality is usually denoted h of k. And the unit group, U of k, is the group of invertible elements of Zk, and which is the same as algebraic integers whose norm is equal to plus or minus 1. I didn't define the norm, but let's assume you know this. By Dirichlet's theorem, again, it's a finitely generated abelian group whose rank is known, R1 plus R2 minus 1, R1 and 2R2 of the number of real and complex embeddings, and the torsion subgroup is finite and equal to the set of roots of unity of K. I think this is the last slide on introduction to number fields. A quadratic field is Q squared T. You can write T as square free integer different from 1. The ring of integers is what you think is Z of square root T when T is congruent to 2 or 3 mod 4, but when it's congruent to 1 mod 4, you have to take A plus B squared T over 2, where A and B are integers of the same parity. And a cyclotomic field is Q zeta, where zeta is a primitive nth root of unity. The main result that we need about cyclotomic fields is that the ring of integers is really Z of zeta, no larger. So, as we say in French, à tout seigneur, tout honneur, algebraic number theory was created in a sense to solve Fermat's last theorem. So let's see how you solve Fermat's last theorem à la Kummer. So, I mentioned that Vent's criterion is probably always applicable. So why would you want another method which is weaker? Well, the main reason is that the algebraic method of Kummer is not only applicable to FLT1, but it's also applicable to FLT2. That, I think, is the main motivation. Forget about Wiles, of course. This was 150 years earlier. So let's use the following notation. Zeta equals zeta p is a primitive pth root of unity. K is the cyclotomic field, zk the ring of integers. Pi is a fundamental element. It's 1 minus zeta, and the principal ideal generated by pi, which I call Gothic p, is the unique prime ideal above p, which is exactly of exponent p minus 1. Gothic p to the power p minus 1 is equal to p zk. So at first, Kummer and other people thought that zk was always a UFD. This is completely false. In fact, it's only a UFD for a finite number of p. One knows the list. But let's reason as if it was. So let's take a p for which it is a UFD. After all, there are a few values of p. So let's assume it's a UFD. Well, I claim that if the first case of Fermat's last theorem is true, but before proving this, I'm going to prove a technical lemma. So I assume that x to the p plus y to the p equals z to the p, with p not dividing x, y, z. Then I claim that there exists an algebraic integer in our cyclotomic field, alpha, and a unit, such that x plus y zeta is equal to u times the power of alpha, the pth power of alpha, u alpha to the p. And the proof is really very simple. As soon as you think of factoring is in cubed zeta, which is, of course, why cubed zeta was invented in the first place. As usual, you may assume that x, y, and z are pairwise coprime. So now we don't factor over z, we factor in z of zeta, and it factors as a product of p factors, x plus y zeta, and so on, equal z to the p. Now, I claim that the factors are pairwise coprime. Indeed, take an element which divides, remember, we are in a UFD, so we're allowed to talk about elements dividing. We don't need to talk about ideals. So it's some element omega divides x plus y zeta to the I and x plus y zeta to the j. By doing suitable linear combinations, you find that it divides y times zeta I minus zeta j and x times the same thing. Hence, it divides zeta to the I minus zeta j because, pay attention, x and y are coprime, but x and y are coprime in z. So if they're coprime in z, they have to be coprime in z of zeta also, because since they're coprime in z, you can write u times x plus v times y equal 1. So this is true in any ring now, containing z. Well, any ring. So that means that omega divides zeta to the I minus zeta to the j, and I mentioned earlier, zeta to the I minus zeta to the j is always a divisor of p in z of zeta. So that means that omega divides p. On the other hand, omega divides one of the factors here, so it divides z. Well, that's annoying, because once again, p and z are coprime in z, in the integers, and also in z of zeta. So that means that omega divides 1. And omega divides 1 means that omega is a unit, which indeed means that the factors are coprime. Good. Well, we're finished for this case. We have a product of pairwise coprime elements, which is equal to a p power. So up to multiplication by a unit. That means that each one is a p power, since we assume that z of zeta is a principal ideal domain, or a unique factorization domain. And this proves the lemma. So this is really very, very simple. Now, as I mentioned, unfortunately, this doesn't happen very often. And this is where, of course, this is why ideals were invented. They weren't invented exactly in this way by Kummer. He introduced ideal numbers. But, okay, now we don't use this terminology anymore. But indeed, let's denote by h sub p the class number of the cyclotomic field. Then the result is that the lemma is still true if you simply assume that h sub p is not divisible by p. That's what's called a regular prime. And let's see why. Well, the proof of the lemma is absolutely identical by changing elements. If you change the word element by ideal, everything works, because what we use is the fact that we had a UFD, that any element can be decomposed as a product of elements in a unique way, and so on. Well, this is true for ideals in a Dedekind domain. So, of course, the proof is exactly the same. So what do we deduce? Well, we deduce that A sub, they're still the factors are still co-prime, and the ideal A sub I equal x plus y zeta to the I z sub k is a p power of an ideal. So A sub I equal B sub I to the p. And the crucial ingredient is that the class number is finite. So since the class number is finite, when you raise any ideal to the power, the class number, B sub I to the HP, for instance, this is a principal ideal. On the other hand, B sub I to the P is a principal ideal, because B sub I to the P is A sub I, which is the principal ideal generated by x plus y zeta to the I. And P and H sub P are co-prime, so you can write P times U plus H sub P times V equals 1. So B sub I itself is a principal ideal. And if you replace, you get that, well, let's take the index 1, for instance. If you write B sub 1 equal alpha zk, then A1 is the ideal by definition x plus y zeta. It's equal to B1 to the P, and B1 to the P, since B1 is alpha zk, it's alpha to the P zk. So you have two principal, well, you have a principal ideal, and you have two generators. You have x plus y zeta and alpha to the P. And when you have two generators of a principal ideal, this means that the quotient of the two generators is a unit. So this means that x plus y zeta is equal to u times alpha to the P. So the lemma is still true. So that's really nice, because that occurs, well, hopefully more frequently. So the rest of the proof, in the case where, don't worry, I'm almost finished. The rest of the proof in the case P does not divide HP is specific to Fermat's last theorem. I won't go into it. It's easy, but it's in the notes. But I would like to add that it uses a crucial additional ingredient, which is Kroneker's theorem, which is a very pretty theorem, which any student in algebraic number theory must know. If you have an algebraic integer, no, otherwise it's completely false, all of whose conjugates have norm equal to 1, this is it's a bad word, have absolute value, complex absolute value, that's a misprint, modulus equal to 1, then it is a root of unity. And in particular, as a consequence, you deduce that if U is a unit, then U bar divided by U is a root of unity. Okay, so what's the power of Kummer's proof for regular primes? So a regular prime is a prime such that P does not divide HP. It's known that there are infinitely many irregular primes, and it's conjectured that there are infinitely many regular primes, and that the density is equal to the e to minus 1/2, which is about 0.6, but this is completely unknown. I think I have to stop here. Well, no, maybe I'll give this slide also. To come back to Catalan's equation, one of the crucial ingredients in the proof was the fact that the HP power of an ideal was principal for all ideals.
We start running way over time.
Way over time? Really? Okay. Fine. Thank you.